Topographic contours appear on engineering and construction plans. So let's make sure we know how they work. What you see here is a plan and a profile view of a hypothetical hill. So let's label those. This top view is what we call the profile view. That is, we are looking at it from the side, as if we're looking at a person's profile. The plan view is the top view, or sometimes we call this a bird's eye view. And what you see here on the profile view is a series of lines that represent horizontal planes. So let's make some sense of this. We'll say we're working in feet for our elevation units. And this line represents an elevation of 500 feet. This line represents an elevation of 550. And I want you to notice there are 5 increments. Okay, so here's this would be 510 feet, 520, 530, 540, and 550 feet. So we say that the vertical distance between any pair of these elevation planes is 10 feet. That is our contour interval. You will see topographic maps that have different contour intervals: 1 foot, 2 feet, 5 feet, 10, 50, 100. And the contour interval is going to be chosen based on the level of detail required in the map, and the scale of the map, and the variation in the terrain. Well, imagine each one of these planes represented by these lines slices horizontally through this hill. Maybe you've been to the deli at the grocery store and seen a meat slicer in action. So I want you to imagine we've got this large galactic meat slicer descending down onto this hill, and the first slice it takes out comes across the top of these 2 little hills. Well, it makes these little slices that you can see down here. And then it descends another 10 feet before taking the next slice through our hills. Well, the next slice farther down is going to trace these lines here on the plan view that I'm tracing with my blue pen. Okay? And then as we go farther down, the slices change, don't they? In fact, notice this next slice down is not 2 individual slices, but it is one big long contour. So I want you to think of a contour line as a line, an imaginary line on the ground that has a constant elevation. That is, if you walked around on this hill, you're walking around, let's say, at this outer contour line, the 500 contour. Everywhere along that line, as you walked, your feet would be at the same elevation. Now, I want you to notice a few patterns in this topographic map. Over here on the left side of our hill, notice in this region marked with my green line that the land is steep. The land surface is steep. So notice carefully here that the contours are close together in that location. Whereas on the other side of this hill, the contours are farther apart, indicating that the slope is not as steep. Please notice that contours can close on themselves just like these did at these hills. Properly drawn contour lines don't end or meet or cross. Did you notice that all of these lines are effectively roughly parallel, aren't they? Notice that these here at the top of the hill, they close on themselves. They form loops. In fact, all of these form loops. However, the contours that represent the ground on your site may extend beyond the limits of your map. Let's imagine this line is the edge of our map. And so the space here to the right of the line does not show on the map. You'll see here that the contours that come up to the edge of the map stop, don't they? So we cannot expect that every contour will form a closed loop on our map. In reality, our map only shows a limited portion of the Earth's surface. Here are three views of one topographic map. In the lower right, we have a plan view showing only elevations. On the lower left, we have the same plan view, but now we have interpolated contours. And on the top of this view, you see an isometric view showing not only the horizontal planes representing constant elevation on the edges, but also the contours as they slice through the landform. All three of these views are consistent with each other. So let's take it apart just a little bit. Let's start down here at the lower right. Let's figure out where the lowest elevations are on this. Well, while I'm thinking about it, 100.75 appears to be the highest. And then we've got, I believe the lowest is over here. And then probably the next lowest elevation is this one here. So these are the low spots. Okay, so if I start thinking about how the water flows, I want you to imagine water falling on this tract, and which direction would it flow? Okay, well, it goes this way some, and then it definitely goes downhill. Looks like it goes this way. And if water fell here at this location, well, it would flow. Looks like it would go this way and that way, wouldn't it? If it fell here, it would fall this way and this way and, well, that way and that way, wouldn't it? It would flow this direction. Okay? So figuring out which direction the water flows has to do with comparing the elevations, and we know that water flows downhill. Well, then let's consider how that's consistent with the map we see over here. Our contours indicate that yes, we have high elevation right where we had that point that's 100.33, and then yes, you will see that water flows perpendicular to the contours. See that? Water flows perpendicular to the contours. Along the edge of the map, notice the contours are nearly perpendicular to the edge. Water will flow downhill perpendicular to contours. Now, the elevations we saw over here on the map on the right are shown to 2 places to the right of the decimal, and we're only showing a contour interval over here on the left of 1 foot. So the contour interval here does not show the elevation resolution, that is to 2 places to the right of the decimal, that we see on the right-hand map. Well, we can still use the elevations on the right-hand map to interpolate these contours. So the interpolation process, let me spell that out, interpolate. The interpolation process really estimates where these contours are based on the data we have. Now, I want you to consider something else. We said that water flows downhill perpendicular to the contour line. So I'm going to switch my color here, and we said that if water falls right here at where it has 96.42 on the right hand map, it's going to flow up to the upper right and then down, straight down. Well, notice what we have is a flow path looking like this. You might say, how do you get that curved flow path? Well, that's part of the interpolation process. But notice where this flow path crosses these contours, the contours form V's on the ground. See that? Do you see this V configuration? And we've got another V configuration here. Well, when we have a waterway, the V's here point upstream. The V's point upstream on any waterway. So watch for that pattern. Here you can see on the isometric view, here is that same spot, and the water flows downhill. Well, notice the flow line goes right through the lowest point, doesn't it? You can see that as I draw it up here. So the flow line, that is the bottom of the waterway, if you trace that flow line, the contours that cross it in a perpendicular fashion, and the points of those V's point upstream.